Hello everyone, this is Singh Shekhawat and today I am back with another video in the series where we were discussing load management system which are designed at Uber specifically. So like in the previous two videos we discussed around QALM architecture, which was the first of the systems which were developed at Uber, and then in the second video we discussed the concepts around Cinnamon. Okay, Cinnamon is a system or a software framework which is used as a load shedding framework in the different services. So basically drop the request whenever your service is under unexpected load. In the previous video we mentioned that there are another two components which we will deep dive into more, and today is the video. Today we are discussing the first thing about the Cinnamon, which is PID controller. So we will start our discussion. Like we mentioned, there were two components, right? PID controller and auto tuner. They have their own functionality to serve in the entire architecture. So today's video is specifically focused on the PID controller itself. So let's deep dive into the architecture. Now to start with, as always, I have created the notes. We will go through the notes as per my understanding, and we will try to understand whatever is written in the entire blog. I will definitely share the link with you of the Uber blog. You can definitely go through it, and then the summary is definitely provided in the video. So again, let's start with the Uber Cinnamon PID controller architecture. What were the key details, or like what are the key principles which are followed in here? What is PID controller? What is the target function? What all these things? So let's get started. Now to start with, what is PID? Okay, it's not a process ID to start with. So PID is not a process ID here. What PID is, it's proportional integral derivative controller. Strong term, but we will try to understand each and every term of this definition: proportional integral derivative controller. Now just to like, let's take a quick example. Okay, this is the diagram of Uber Cinnamon architecture which we discussed in the previous video, but let's take a quick example here to give a head start to our video today. So take an example of any car you drive. Okay, any of your favorite car. So there is a feature called cruise control in most of the modern cars. Now how cruise control is helpful is, let's say you are driving on a highway. Okay, you are driving on a highway, and you want to maintain a speed of 80 kilometer per hour, or you are driving maybe on mountains, or like whichever place you like. Okay, so you want to maintain a constant speed. Now to maintain that constant speed of 80 kilometer per hour, you will have to increase or decrease the power which you are providing to the vehicle, right? So because if let's say uphill and you still want to maintain the 80 kilometer per hour, you will have to give more power to the engine. If it's downhill, then you already get that acceleration, so you can reduce that acceleration from your end. So that's the feature of cruise control. Okay, either you manually do it. Now you are manually increasing or decreasing the power by putting up your leg on the accelerator. The feature cruise control is helpful in a way that it does it automatically. Okay, तो आपको नहीं करना पड़ेगा वो basically. If you want to maintain, let's say you are at a speed of 80 kilometer hour, you press that button. Like most of the car, it's a button in the steering, or like at the side of the window, that you can press and the cruise control kicks in. Okay, so in this scenario you don't have to do anything. Okay, unless you press your leg on brake or something, the speed will be maintained and it will automatically adjust that power needed. That is what is your PID control. That is the job of the PID control. How basically basis how it does that. We will try to identify that equation basically. Not the entire equation is not in the scope of this video, definitely of the entire PID, but we will get in the lower details and the target function specifically, which will help in our main problem. The main requirement of the PID controller is, I want to identify the percentage of request which needs to be setted, which needs to be dropped. Okay, so I hope you are clear with the basic idea of what PID controller does. So what is PID controller? It's a control loop mechanism. Given some feedback, continuously tries to make a calculated error value, which is defined as ET, called a target function go to 0. Cool. So this is the kind of definition. Go to 0 as in, like, let's say I want to maintain 80 km per hour. So when I say I want to go to 0, so it is 80. What extra I can apply that it can come back to 80. Like, it should not reduce or it not increase. So that's what is PID controller, and the main problem here is figuring out a target function. Okay, this calculating an error value ET called a target function. How will you identify this? So the main discussion point of this video will be identification of this target function. You can go through this Wikipedia article. It has lot more details around the PID controller, right? We have used that concept in developing the software system, but it is heavily used in the mechanical systems. Like, one of the features which I mentioned is cruise control, and there are a lot more details there, so you can definitely check out that Wikipedia article. But in the scope of the Cinnamon architecture, let's go ahead. So from the previous diagram, or like whatever we had, our main framework of the entire end-to-end flow of Cinnamon, quickly summarizing it, you ensure the priority, that priority is there attached to the request. If not, you assign it a default priority. Rejector, it basically checks if the request has to be rejected or not. PID controller provides that feedback to the rejector. If it is the request is accepted, it is added to the priority queue. Okay, once it is added to the priority queue, based on the in-flight limit, the requests are scheduled and then sent to the service handler or API logic or API handler of that service. Cool. So this video specifically, as I mentioned multiple times, is focused on PID controller. Next video we will be discussing auto tuner component. Now let's move ahead with the architecture. Goal of the rejector. What is the goal of rejector? Reject करना है. What is the goal of rejector? Reject करना है. So figure out how many requests should be shredded, rejected, dropped. That is the main goal of rejector component. And NFR, the main critical NFR of this entire function, of, like, not the entire function, entire system of Cinnamon, is that this system should not add too much overhead to my business logic, basically. Okay, so the request arrived at a system endpoint, or you can say your load balancer, and then let's say it goes through the Cinnamon layer, framework layer. So you are doing some programming logic there, right? So that should not take much of the time. The overhead should be too less, and in last video we mentioned it's around 1 microsecond, so we are good there. Okay, so that's what we are saying. It should not impact our API latencies, basically. Okay, cool. So rejected module has two parts. Rejector module has two parts. What are the two parts? One part is, do I have to accept the request or do I have to reject the request? Okay, cool. So you read the priority of the request. If the priority is lesser than threshold, reject it. If it's more, then accept it, basically. Okay, so this is simple if else logic. Simple if else logic. I have the priority in my, let's say, some global variable. Not the priority, the threshold value in my global variable. Each time a request comes in, I check the priority of that request against the threshold. If it's less, then directly reject it. If it's more, then accept the request and then forward it further to be added to the priority queue. Then later on it is added to the scheduler to be processed by the service handler. Okay, second component, which is the most crucial for, and that's where the PID controller helps us to figure out that logic of percentage of, like, how many requests should be shared. It's the offline component. So it runs simple, a cron job, you can say. It runs every 500 milliseconds. Okay, this is a configurable value, definitely, but in the Cinnamon's current architecture, it's 500 millisecond, and it tries to figure out the threshold. So what it does, it tries to it verifies if the endpoint is loaded, and if loaded, what is the percentage of request that needs to be dropped. And PID control operates on two factors. What are the two factors? First is incoming request to the priority queue. What are the number of requests that are added to the priority queue? And the second factor is outgoing request from the queue into the service handler. Okay, cool. So these are the two factors on which the PID controller operates. Now, coming back to the PID control logic, we took the example of cruise control, right? So we already discussed that we want to maintain that same constant speed. We already took that example. Now let's go little bit into the details. We mentioned PID stands for proportional integral derivative controller. So what are those terms? So these are the three parts of the PID controller. One is proportional, second is integral, third is derivative. What is proportional? Proportional is difference between target value and current value. So in our cruise control example, it's target speed minus current speed. Okay. So your target speed is let's say 80 km per hour and your current speed is 60. So 20 is the difference. That's the proportional value. Integral is sum of historic p values. So over a period of time, whenever your car started, right? What were the values of this p value? P is target speed minus current speed. And in case of cinnamon architecture, it only considers for last 30 seconds. And this is, there are a lot of configurations, right? 500 millisecond is one configuration, this 30-second is one configuration. These all values are figured out based on the load testing which is done after the system is in like after the system is developed. So like all the constants, or like what kind of values we should have in our system. Those are the configurations which are came up after the load testing and how system performs well. So in case of cinnamon, it only considers last 30 seconds, figure out based on load testing, and works well with changing request patterns. When I say changing request patterns, it means that I have different kind of services. In the single service as well, the request can go up and down. Like there is sometime it's peak traffic, sometime it's a low traffic and median traffic and all those things. Cool. Derivative, the third part is derivative in the PID. D means derivative, rate of change of p, how the p is changing. Okay. And it is again not considered in case of cinnamon architecture. And again, as I said earlier, right, if you want to get details of entire PID controller and how it is implemented, right? So Wikipedia article is the starting point which you can refer. It has the equation details and a lot more details more than what is covered here, and which is more specific to that. This video is more specific to cinnamon architecture. Now, and your PID value is weighted sum of all the three terms. These all three terms are, these are basically constants which we mentioned right now, Kp, Ki and Kd. Okay. Now we mentioned PID controller as a feedback loop, right? Okay. So what does feedback loop means? Feedback loop basically means you do something, you provide the feedback, you update the threshold, and then based on that threshold you pass on that. Again, if the threshold is less or more, again you provide that feedback, and then it's a circle basically. So you have your, like referring from the diagram, you have a overload indication. Okay, you figure out this pt value. We will discuss how we will derive this pt is basically your target function. From this pt you derive p, I and d. pt is calculated using request throughput, and we will go into the entire formula how we will calculate pt. And as I mentioned earlier, this is our key discussion in this video, how you will calculate the target function or error function. Okay, now you calculate p, I and d terms using pt. Result is forwarded to cinnamon module or cinnamon framework, modifying a change needed to request throughput. Now the calculation of pt, calculating rejection percentage, load shedding percentage, or pt. How will you calculate it? So what is the goal of PID controller? Keep outstanding queue at minimum, minimizing queue time. Okay, so the queue size which you have to maintain it at a minimum. When I say minimum, you don't have to do it as 0 or 1, because that will hamper our service utilization. We also have to ensure that your service is heavily utilized. Like let's say you're using m4.large instance, so if it is able to serve 10 requests, you should strive for serving those 10 requests. Okay, so that's why the second point comes in picture, which is keeps concurrently executing request at a limit max utilization of service. So you have to ensure 2 points basically. First is that you keep the outstanding queue at minimum. Okay, along with this, you have to also ensure that your service is maximum utilized. Whatever is possible at that particular moment, you have to ensure that your service is maximum utilized. Now what are these point corresponding to? I already mentioned point 1 focuses on rejecting the request, and point 2 puts back pressure on point 1 that's not so many requests are rejected, keeping service utilization as maximum possible, right? As I mentioned, If you just focus on point 1, you might reject all the request and you just keep the queue size to 1, that you are happy, yeah, I'm keeping the queue size to minimum. But that's not only thing we want. We also want our service to be maximum utilized. Whatever resources I have, I want to test that CPU utilization to maybe 95% or 90%. Cool. Now the diagram, these are the things which we will consider in our architecture. So you have scheduler has multiple requests which are placed in the priority queue. So you have a request queue, you have, let's say, 3 requests which has priority 200, 300 and 700. Then they are moved to the service. Okay, so service, let's say, has an in-flight limit of 5. We discussed all these terms in our last video, and I highly recommend that you watch the video before this one, or at least read the blog before watching this video. So you have 2 free slots and 3 of the requests are in processing. Now in this, as like discussed here, in-flight request limit, this is calculated by the auto-tuner component, which we will be discussing in the next video. In processing are 3, and in outstanding, which are in the priority queue, you have again 3 requests. Now this is the final equation which we will come up. We will discuss how we are coming up with this equation, but the final equation is, you have in that particular time frame, t is basically your time. Okay, let's say you are taking 30 seconds, you are taking 500 milliseconds, or whatever time you are taking, so that's the time. So number of requests which are into the queue. Out basically means number of requests which are out of the queue and pushed to the service for processing. Free in flight, we will discuss why we need this term, and then we have out apostrophe wala, whatever you say, right? So that we will also discuss why do we need that. So if I talk about free in flight, it's in flight limit minus current number of in flight request. So we will discuss again why do we need all these things. So the simplest form could be in this architecture, or not the architecture, the equation itself, right? The simplest form is that your PT is derived based on these two values. Okay, number of request incoming minus the number of request outgoing, as we discussed right earlier, somewhere here. Incoming request to the priority queue, outgoing request from the queue into the service handler. Now why do we need other things? So let's talk about it. Okay, so the simplest form of equation is in minus out. Okay, number of requests which are coming to the queue minus that number of requests which are popped out of the queue and then pushed to the service handler. Now we also have to consider the service utilization, right? We mentioned that we have to consider the service utilization. Okay, you can't make the queue size as 1, okay, or 0 and say that, yeah, my queue size is kept as minimum. 0 is 0, doesn't make sense. 1 you can, but so let's say your in is greater than out. So these are the basic scenarios. If your in is greater than out, then you increase the drop request. If your in is lesser than out, then you reduce the drop request. If in is equal to out, okay, but the number of requests might be too low. Okay, if in is greater than equal to this scenario, right? If in is equal to out, this means whatever request I am sending to the queue, they all are processed basically. Now we mentioned again, I think I'm repeating it again and again, but we have to ensure on focus on the second point as well, that your service is not underutilization and your all the resources are utilized. So to figure out the load shedding ratio, we consider the service utilization, and that's why we take free in flight into consideration. What is free in flight? It is basically unused in flight spots. Okay, what are the spots which are available? So if you go into this diagram, these are the 2 slots which are available, right? We don't want this scenario to happen. We want that all these requests are processed. If the in-flight limit is 5, then I want to ensure that my queue sends those 5 requests for processing. Okay, so your free in flight is equals to in-flight limit minus current number of in-flight requests. So it is basically 5 minus 2, which is 5 minus 3, which is 2. Okay, so this is your free in flight. Now in case of in equal to out, there can be 2 scenarios, right? Either your free in flight equal to 0, all the requests are, I mean, the whatever your in-flight limit is, you have provided all the, that number of requests. So this means that your service is working well, right? It's fully saturated. Okay, so number of requests going into the queue and number of requests out of the queue, and you are utilizing that entire limit which is available to the service as per the utilization. So this is great, but what if it's not 0? In that case, P will become negative. As per our equation, P will become negative and it should drop more request, okay, to ensure that our service is working as expected and the load is not increased on the system. Now, another thing is, we discussed that we have to ensure the maximum utilization of resources. Other parameter which we mentioned at the start of video is that there are different request patterns which are there present with the services, right? And there are different loads which are served by the services, and that's where your out parameter helps. Now how it helps is, uh, we take a normalized value basically, okay? So it is normalized with the number of requests in a particular period, okay? And like what is the number of requests which are going to the API handler basically, okay? So if the number of processed requests equal to 0, this parameter out apostrophe, okay? So in that case, either it is I think I mentioned it somewhere. Yeah, so if it's not, out is not 0, okay, so in that scenario the out apostrophe is equal to out only, and in case it's 0, okay, so in that scenario it is normalized to uh, the in-flight limit whatever we have. So in that case, like in-flight limit is 5, so it is will be normalized to that, okay. And if you have a positive value for out, then you use that value. So all these factors we discussed are combined into this, and this is what we have as a final equation that is used as a target function or a error function et, which we defined earlier, like to the start of the video, that how can you make it 0 so that you get your desired output. Now talking about implementation is fairly simple. You just need two counters, right? You just need two counters. What are the number of requests which are going inside the queue, and what are the number of requests that are popped out of the queue, and your counter has to be atomic counter, right? There should not be any race conditions. So your in is increment counter when request enters the queue, out is increment when request exits and forwarded to the service handler. And there are some constants involved, right? KP and KI. Based on load testing, you have figured out as, and these are from the blog itself, based on the load testing, you have 0.1 and 1.4 as your constants. If you quickly want to check out the equation, we have it somewhere, yeah. So go through this blog, you will see these constants, right? KP, KI and KD. KD we are anyway not using, but KP and KI. So the const, and this is the ET we already calculated, right? So just to figure out like what the value of these constants you have figured out based on the load testing, and these are the values which I have to fill in the entire function of PID controller. Now another thing is that how will you calculate that setting threshold calculation. Now we mentioned that the rejector module use PID control, right, to calculate priority that needs to be set. Now how will you do it? How will it do it? So it will keep the track of last requests, let's say 1000, along with their priority, what was their priority, and then let's say the threshold is set to 10%. So it will use that cumulative priority of those last 1000 requests or whatever configuration we have to figure out a threshold. So based on those values you figure out like what is the priority, and based on that you have to figure out what it tier belongs to, okay, what are the requests which it tier belongs to, and what is the cohort basically. In the last video, if I quickly summarize it, we mentioned that we try to figure out a cohort of users whose request should be dropped, so that not always all the same users are impacted, to ensure a smooth customer experience. Cool. Ending the video with how the testing was done for this PID controller, and you do a load testing with different request patterns. We mentioned that we came up with different configurations as well, like 500 millisecond, 3 second, 30 second was one of the configuration. Then we had a constant value of KP and KI, which was 0.1 and 1.4. So all these things you figure out based on the load testing you do on your system or for different request patterns you are serving. And then you also perform like how fast your PID control reacts and figures out a stable rejection limit, okay, without adding overhead to the system. Cool. So this is all about today's video. I hope it made sense. You are able to extract some information from it. We will meet again in another video. We will be discussing auto tuner. Till then, stay safe. Tata. Bye bye.